vi börja. Ja, då kör vi. Okay, let's start. Welcome, ladies and gentlemen, to this public PhD defense at Mid-Sweden University. My name is Professor Mikael Gidlund. I will be sharing this dissertation. Today, Mr. Simone Grimaldi will defend his PhD thesis towards radio environment-aware IoT networks, wireless coexistence methods for low-complexity devices. Except for Simone, we have 4 other very important persons with us today. We have the opponent, Associate Professor Georgios Papadopoulos from IMT Atlantic in France. Welcome. And we have 3 members of the grading committee. First, I would like to present Professor Havinga from Universitetet Twente. Welcome. We have Associate Professor Niclas Björsell from University of Gävle in Sweden. And finally, we have Dr. Wiklundh from Qamcom Research and Technologies. She has been working 20 years with robust wireless communication. So welcome. I will briefly basically mention how the process is, and then we will move onwards with a presentation from Simone. So first of all, the respondent, Simone, will present his work, maximum 40 minutes. After that, there will be a short technical break, maximum 5 minutes. After that, there will be the discussion part with the opponent and the respondent. And when the opponent is ready with it, or has finalized all his questions and is satisfied, we will move on to the 3 members of the grading committee, and when they are satisfied, we leave the floor open for the people in this lecture hall, and after that, for those who might have a question that is logged in on Zoom. So, before we start, I would like to ask Simone, would like to defend the thesis as it is, or do you have some amendments?
I would like to defend the thesis as it is.
Okay.
Thank you.
Thank you very much. And by that, I leave the word to Simone to give a presentation.
Perfect. Thank you, Mikael. And I would like to thank and warmly welcome the opponent and the members of the graded committee. I also welcome the audience that has joined today and the audience that is following remotely. I am very glad to present the result of the research work that I carried out during my PhD studies at Mid-Sweden University, under the supervision of Professor Gidlund, Dr. Mahmood, and Professor Zhang. And this work covers the development of methods for radio environment-aware communication in IoT networks. First, I would like to start with some introductory concepts on the relation between Internet of Things and wireless communication. To begin, what is the Internet of Things? Well, we could agree. Okay. No problem. Screen one?
I think if we take Zoom on to get on this screen instead. Bring down Zoom. Bring it back here. Yeah, and then stop presenting. It should be working.
gjorde den? Vart tog den vägen?
Okay. Thank you. Okay, small delay, we'll try to recover. And let me resume the discussion on the introductory concept on the relation between IoT and wireless communication. And we need to define what is the Internet of Things. The definition of Internet is quite known to everyone, but what are the things in these pictures? Well, in this broader definition, it can be virtually anything that is interacting with the physical environment. The definition covers, for example, a sensor node connected to an industrial process rather than domestic appliance, a smartwatch or sensor in the smart grid. All these objects heavily rely on wireless communication that is needed for bringing the connectivity to this object. Internet of Things market has a high growth rate. There is already in 2019 the number of IoT connection were around 11 billion, and it's estimated to ramp up to 25 billions of IoT related connections in 2025. IoT wireless communication is a cornerstone of IoT, and there are several available wireless solutions suitable for IoT that can be categorized with respect to two main characteristics: the physical area covered by the network and the frequency band that is used. We have wide area network and or local area network, and licensed spectrum usage versus unlicensed spectrum usage. The focus of this work is on local area communication over unlicensed bands. So why is it so interesting and so convenient to transmit over unlicensed bands? Well, it is cost effective. There are no operator related costs. There is worldwide applicability of wireless solutions, as most of these bands, such as the ISM band, which are bands for industrial, scientific and medical applications, show very few changes among different countries and regions. And this leads to a quick and easy deployment of devices and networks. There are few challenges which are mainly related to interference. There is interference from co-located wireless networks. There is interference in some bands from the emission of electrical devices, electromagnetic noise. And this makes fulfilling a strict quality of service requirement potentially challenging, especially for critical IoT applications. An example of critical IoT applications are industrial applications, for instance, industrial process automation. This table shows that the quality of service requirement can greatly vary even within the same application domain, ranging from non-critical for monitoring applications to often critical for control system, closed loop control, up to always critical for safety applications. There are compromising factors for short-range communication for IoT over a licensed band. These are mainly related to two families: the radio propagation issues and radio frequency interference. Regarding radio propagation, there is a broad range of propagation conditions even within the same application domain. For example, industrial applications, there are several different radio channel characteristics as several different environments with different properties. There are also often time-varying environments with moving obstacles and leading to frequent non-line of sight communication. And there is there can be significant multiple fading with waveform distortion and intersymbolic interference. While intersymbolic interference can be seen as the interference of signal with itself due to the echoes of the radio environment, there is interference also from external radio system, and this interference is nowadays ubiquitous as the diffusion of IoT is extremely pervasive, and there is also a significant performance impact of cross-technology interference reported in the literature. Scientific literature has shown that this cross-technology interference impact is strongly asymmetrical. In the picture, we can see the three main players with respect to the wireless technologies, which are 802.15.4, basis of wireless sensor networks, 802.11, which is the basis for wireless LANs, and 802.51, which is the basis for Bluetooth systems. In this picture, 802.11 networks are the most challenging to coexist with due to a high data rate and bandwidth, and also due to this ubiquity. Just let's think of how many 802.11 devices we are using at this moment in this room. And so what is the research objective, and what is the target domain of research? Principal objectives are two: the development of lightweight methods for radio environment awareness and exploiting this method of radio environment awareness to improve communication reliability and coexistence of wireless networks. The target domain are critical IoT applications with industrial IoT as the study case, but the method have also potential wide applicability for IoT over non-licensed bands due to the escalating wireless interference. The objectives are first keeping in mind two important constraints: that the developed methods should run on resource-constrained IoT devices. IoT devices are typically very resource-constrained with limited processing power and radio limitations as well. The second constraint is that methods should be executed in runtime in IoT networks. These objectives have been mapped into two research questions, and the first research question covers the runtime monitoring of the radio environment and is subdivided in three sub-research questions: the detection of communication blackouts, the methods for interference detection and identification, and methods for spectrum and link state analysis based on single packets. And research question 2 instead exploits the method developed in research question 1 for improving communication reliability by interference mitigation, which is the first sub-research question, and mapping interference and enhancing wireless coexistence. The research methodology of this work is a mix. It is experimental modeling and simulations, and a large part of the works have been tested experimentally by implementation on resource-constrained IoT devices and testing in relevant environments. Often mathematical models have been developed to explain and predict the performance of the developed methods. Finally, the simulation-based approach has been used in some works. Some details about the experiments, about the hardware and the experimental locations. Strongly resource-constrained 802.15.4 nodes have been used in the form of Telos-B wireless nodes, which is a fairly old 802.15.4 platform. Some auxiliary devices have been used to find ground truth of interference in several environments or for baseline analysis. These devices are software-defined radios, portable spectrum analyzer, as well as commercial off-the-shelf devices which have been used for cross-technology interference generation. Regarding experimental environments, the environments are fairly representative of the selected use case for general IoT, for example, in office environment, but also for the industrial IoT, as the several experiments have been carried out in industrial facilities or semi-industrial environments. The research questions have been addressed via 7 research works. 6 of these research works have been published in journals and conferences, while paper 7 is under review in 1 journal. It's in advanced state review. Regarding the first research question, radio environment analysis, why is it particularly relevant in modern IoT? This is relevant because it can ensure adaptivity to harsh time varying environments for IoT networks, and coexistence techniques in presence of massive cross-technology interference can be deployed. Nevertheless, the IoT radio platform imposes several processing and sensing limitations. These processing and sensing limitations are limited memory and slow processing, leading to long processing delays, for example, and these are more on the processing side, while there is also a limited sampling rate and the availability of radio frequency energy samples only in their heavily filtered version, which is RSI, the received single strength indicator. Slow frequency switching and fixed channel filtering are also other limitations for the radio point of view of this platform and might hinder the analysis methods that require fast frequency switching and fast spectrum scanning. The first method developed in this work are methods for interference identification, and the investigation is about how to use RSI data for performing in-depth interference identification. This is important for effective mitigation techniques, as said, and many of the concurrent approaches literature are often parts of two sets. One set is using long sensing times and using COTS IoT devices. The other approach is instead using specialized hardware and sampling at a very high sampling rate and adopting more advanced signal analysis approaches. The first method in this context is a supervised learning-based classification method employing supervector machines. Multi-class supervector machines are trained based on signal feature extracted from RSSI sample traces. Amplitude and temporal features are analyzed, and three classes of interference, the 802.11 networks, microwave ovens, and interference-free channels are characterized. The results have shown the reasonable accuracy, while the spectrum sensing time has been shown to be quite limited, around 200-300 milliseconds. The method doesn't really gain from having longer sensing time. And the effect of uncalibrated devices on classification accuracy is moderate. So while these results are encouraging, they do not provide full on-device ID. While, for example, the sample window is particularly short, 200-300 milliseconds are a short sensing window. Anyway, the RSI sample trace need to be stored, need to be processed, which can be problematic with the results constrained nodes. Also, the SVM exceeds the processing capability of the target platforms, which means that the RSI trace might need to be sent over the network for offline processing, which is certainly not ideal in resource-constrained networks. And another limitation is the network cannot use the channel during the sensing time, which limits the schedulability in terms of lot and channel lumping networks, for example. And these limitations arise from the fact that only the main source of interference is recognized per sensing round. We tried to address this problem by developing a method for interference detection and identification which works on single burst. In order to do this, strong features need to be extracted from the signal burst in the form of spectral information. And this is particularly problematic as it is hard to execute FFT both for radio limitations and processing limitations. The consequent separation of the spectral feature would enable an easier classification. The method for overcoming the FFT problem is the following. During the lifetime of a signal burst, two sideband samples are acquired by quickly steering the local oscillator, the frequency synthesizer on board of the nodes, and these samples sampled on the lower sideband and on the upper sideband bring information on the spectral distribution of the signal. Then the sampling is prosecuted on the central frequency to extract some envelope-based feeders. Some of the advantage of this approach is that it enables the use of lightweight classification architectures. As the interference classes are more separated in the feature space, there is an expansion of the family of classified technology, which includes also 802.15.4, for example, which is the network technology that is overrated sensing in the experiments, which in turn means that there is no more need of a silent slot during sensing. The network can keep transmitting as the bursts are identified and classified. And this approach leads also to the extraction of technology-specific statistics, as the different interference sources are separated in an extra dimension of the radio space, which is the technology interference dimension. The classification architecture, different classification architecture have been tested, and we have evaluated the advantage of more complex architectures, such as neural networks with respect, or supervised machine with respect to simpler classification trees. And the good news from this analysis is that classification trees with moderate depth can ensure a good classification accuracy and can be implemented in real time, even on this very old TLSB platform. And the other good news is that execution that can be ensured in real time with an execution time that is comparable to the duration of the bursts themselves and particularly bounded in time, less than 1 millisecond. The subsequent idea was to extend the concept of spectral features to perform a comprehensive spectral analysis still based on the burst of interference technologies. And the idea is that this kind of approach of extracting spectral features during the burst duration would need specific swept-tuned spectrum analysis in employing spectral patterns that need specific optimization. The idea for employing this approach is that while supervising learning works well when the format of the signal is known, the format of the interference technologies is known, the interference technologies evolve month after month, year after year, and there might be some signal formats that are not recognized. There might be jamming devices or other forms of noise. In this context, bus-based spectral analysis can enable fast interference, avoidance, and unsuper learning-based flavor kind of classification approach. The modular solution that is proposed pivots on intra-burst sampling patterns, which are the blue part of the picture. And in this picture, the first section of the model performs burst detection and intra-burst spectrum sampling. So spectral sample on the complete on a region of the spectral bursts are acquired, and then the onboard microcontroller processes the traces and estimates central frequency and operates a spectral reconstruction, a model-based spectral reconstruction. Then the use of the information is particularly interesting in approaches for adaptive frequency hopping, which we will discuss later in this presentation. Some selected contribution of this paper. The contribution of this paper is not only limited to implementing the whole machine inside on a wireless node, but it's also defining an optimization method for finding minimal error sampling patterns and to find a closed form lower bound for the mean sampling pattern error. This parametric error modeling allows easier platform-specific optimization so that by inserting in the problem the characteristics both on radio and processing side of the target platforms, specific and optimized spectral patterns can be obtained. And there is evidence that optimized spectral patterns decrease, in fact, spectral distortion, allowing the use of more lightweight reconstruction methods with the advantage of faster processing on resource-constrained devices. Another approach in the context of radio frequency analysis is the link state classification. For wireless nodes in unpredictable radio environments, it's really important to keep track of the properties of the radio link. The properties of the radio link are completely described by the frequency response or the impulse response of the channel or the time-varying version, but computing this impulse response at runtime is particularly complicated, or if not impossible, for different reasons with resource-constrained devices. The idea here is that instead, line of sight, non-line of sight state could be classified, and this classification could be done on a packet basis, which would lead to fast link state estimation and lead to rapid adaptation of transmission parameters. In order to do this, dual radio measurement has been deployed, and the effect on the quality of the energy samples on the classification accuracy has been analyzed. The results show that the 802.15.4 SSI processing, which has a low-pass filtering effect for different concurrent effects, has a significant impact on classification accuracy. And the paper also investigates that the advantage of modifying the SSI calculation strategy, for example, the moving average filter, which is a part of this processing, or the bit depth to enable higher performance link state classification. And this might be used, for example, for defining a better RSI indicator for signal analysis purposes. which is not available today in 802.54 nodes, for example. The last work on grid environment analysis covers the monitoring of end-to-end communication. Time-slotted mesh networks are commonly used in industrial applications for process automation, for example, and wireless ART is one of the main standards. And this paper has analyzed the effect of communication blackouts and the reaction of the network of the wireless ART standard to communication blackout, which are particularly dangerous in the terms of communication reliability for the end-to-end communication. And the paper investigates a fast, accurate blackout detection as a key for reestablishing the communication. The mechanism proposed is based on transport layer acknowledgement and monitors the traffic with actuators in a mesh network. Different detection methods are here tested in simulation-based approach, and a closed form expression for the worst case blackout detection delay is derived, and the analysis covers the search for a trade-off between a false detection rate and detection delay. The second research question of this work covers the usage of the method used in the first part for interference management, for interference coexistence of wireless technologies, and for improvement of communication reliability. The first work in this sense covers the usage of spectrum analysis in proactive interference avoidance techniques. And the idea is that time-slotted channel hopping is a common technique used for interference mitigation in ISA 111A or wireless ART, for example. And in these approaches, the channel blacklisting can also be adopted, as a channel is blacklisted after quality of service drops on some links or channels. And the device in this approach, which is a reactive approach, the devices might undergo communication blackout or heavy performance degradation if heavy interference is acting on a specific link in a particularly disruptive way. The idea is that the developed method for spectral estimation can be used in this context, as the spectral estimation is available within a few milliseconds after the detection of the interference burst. Then a spectrum criticality map, which has a higher resolution than the channel width of the target technology, can be created and updated at runtime. And this representation maps the level of risk of transmitting on a certain sub-band of the spectrum. And the information can be therefore used for blacklisting of wet listing of channels in a very fast way on a link basis and in a proactive manner. The effects of these blacklisting techniques with respect to simple time-slotted channel hopping approach has been tested in a wireless link implementing the ISA 111A time-slotted channel hopping patterns, and the real-time performance monitored with and without the SEAB, which is in this case the spectrum estimation and anticipative blacklisting mechanism, which is the name that we have given to the proposed solution. And what can be seen from the image is that when the interference source starts acting at affecting the link at T1, while the time-slotted channel hopping somehow mitigates the effect on this very heavy in broadband interference, but the performance drop is significant during certain times as the time-slotted channel hopping sequence crosses the interferer channels. Instead, due to quick blacklisting, the problem is addressed and these channels are blacklisted. This is particularly interesting as the interference is here not static but is moving in frequency. So the SEAB mechanism is able to track the interference and find the spectral footprint, which is time varying. The techniques gives also an important reduction of consecutive transmission failures, which are particularly important in critical communication, and it leads to an over 70% reduction of the worst case duration of communication blackout, with an important reduction also on average. The channel-specific packet delivery ratio, calculated in this case as an average over the whole experiment, is also boosted with just a limited imbalance of channel utilization, thanks to fast blacklisting, so that the status of the blacklist table reflects the current criticality level of the channels. The last work in the context of cross-technology interference avoidance and cross-technology interference coexistence is the work on interference mapping. The on-device interference detection and identification methods is here applied at the network level to map co-located wireless networks. This approach has several advantages, as the map is obtained with COTS devices only, an in-depth representation can be available localized at the network device. And this representation includes time frequency and technology dimension, while the space dimension can be added via interference data aggregation. The developed method has been implemented in a IEEE 8254 star network, which has been deployed in an office environment and kept running for around 42 hours. The result is that the network is able to separate the effect of two coexisting wireless networks, which are the 802.11, 802.51, and this map particularly shows a snapshot of 15 minutes where the power distribution of the two interference families is separated on the z-axis here, which represent the interference dimension of the radio space, the interference technology dimension. The interesting thing here is that even if locally the devices have an extremely well mapped version of the interference in time and frequency domain, only the relevant information is sent to the network controller for aggregation, which limits the data that is sent to the network and allows a lightweight interference report, which can be fit in a 8254 payload, also leaving space for further payload information or network overhead. The use of interference mapping are several and changes with respect to the time horizon. In the short time horizon, so in the range of milliseconds, the interference detection identification can be used locally on a link, for example, for white space prediction or adaptive frequency diversity, which is the mechanism discussed beforehand, for example, or the medium time horizon interference-aware routing with the quality of service management can be also adopted, for example, prioritizing different data flows with different criticality levels. And on the long time horizon can be very useful for network planning and troubleshooting and for the analysis of big data regarding the centralized collection of interference data. The third approach is tested in paper 4, which analyzes which covers the performance estimation of a Bluetooth mesh network under different network settings and real environment conditions. Specifically, the performance of the network is estimated in a simulator in presence of interference, which is mapped using the ID method. So it is originating from the mapping strategy. And the 802.11 interference, which has been mapped in the previous work, is used here to predict the effect of cross-technology interference in time, frequency, and space. The results are the estimated packet loss rate varies significantly with respect to channel and to time of the day, and since only 3 BLE channels are used, there is a limited frequency planning and a limited possibility of ensuring good frequency diversity here. Still, it is absolutely interesting to see how the complex dynamics of the IO211 networks distributed on an office plan can vary greatly with respect to this domain, so with space, with frequency and time, and how this variation can greatly influence the performance of the network. The recap of the research work with respect to research questions and findings. The first research question has investigated methods for radio environment analysis. Burst-based interference detection identification in real time has been deployed, and spectral analysis of signal burst has also been addressed. the classification of line of sight and non-assigned links on a packet-based has been analyzed, and the detection of communication blackouts based on end-to-end acknowledgement filtering has been tested. The research question 2 instead uses the results of the arising from the investigation of research question 1 for ensuring proactive time-slotted channel hopping adaptation to boost the reliability of links under heavy wideband radio frequency interference. Second, the interference detection identification information is here used for cross-technology interference mapping, and it is shown that this interference mapping is feasible even of strongly constrained IoT networks. Then the potential use of interference mapping to study the wireless coexistence and network planning in presence of several co-located IoT technologies is also shown. The research has attempted to address both research questions in the most comprehensive way. Nevertheless, some research gaps are left for future research, and particularly research question 2 is broad, and more solution for coexistence reliability enhancement, which are based on the methods of developing the addressment of research question 1 can be done. Also, the methods in research question 1 do not investigate the role of energy efficiency, sensing, and signal analysis. And some direction for research extension based on these research gaps are comprehensive scheme for detection and re-establish communication in the end-to-end communication in time-slotted channel hopping mesh networks, methods for cross-technology interference avoidance, which are based on the estimation of the cross-technology impact based on the knowledge on the physical layer of the interfering technologies, and the evaluation of the advantage of employing cheap error patterns in enhancing the strategy for classifying line of sight and non-line of sight links. Thank you for the attention.
Thank you very much, Simone. We will have a short technical break, and we will be back in 3 to 4 minutes for the discussion part.